Hello and welcome back. My name is Dr. Mark Taylor. This is the Delaware Tech Physics 111 Lesson 5, Part 2. This is part of the second lesson of Unit 2 on forces and energy, and it's a continuation on the section on forces, Part 2. So where we left off here, we're now on forces in terms of whether they are balanced or unbalanced. Now, what does that even mean? Balanced means where you have multiple forces and they've canceled each other out, so that the net force, the sum of the forces, is essentially zero. Forces are acting in opposite directions or in some combination of directions where they cancel each other out. If they don't completely cancel each other out and there's something left over, we say the forces are unbalanced. And another way to say that is our net force, or our sum of forces, is not zero. It actually has some value. And if you have a net force that's not zero, you also have an acceleration of that object that those forces are on that is not zero. In other words, if you have forces that are not balanced, the object will have a net force on it and the object will accelerate. Okay. So horizontal net forces and vertical net forces are typically analyzed separately, that is, independently. We look at all the horizontal forces or components of forces in the horizontal direction. We analyze those. Then we look at all the vertical forces, the up and down forces, and analyze those separately. And if the forces are completely balanced in either direction, we say the net force in that direction is zero, and that's referred to as equilibrium. So let's look at these questions. Number one, when an object initially at rest experiences a net force of zero, it will what? Well, if it's at rest, that means it has zero velocity, and if it has a net force of zero on it, that means there's no residual force acting on the object. It means all the forces are balanced at this point, and there's nothing left over to accelerate the object. As a result, it will stay at what it was, which is at rest, and therefore it will remain at rest. Remain at rest. In other words, if it had a velocity of zero, it'll keep having a velocity at zero because there's no net force on it. All right, number two. When an object initially at rest, all right, it's not going anywhere, its velocity is zero, experiences a net force in a particular direction, it will, all right, so this time there actually is a net force acting on this object that starts off with a velocity of zero. So it will start accelerating, it will accelerate, it'll go from zero to something, and it will accelerate in the direction of the net force. Acceleration is always in the direction of the net force. That's right, force sub net. Okay, it will accelerate in the direction of the net force. And in this case, because there is a net force, it's not zero. By definition, the forces must not be balanced. Otherwise, if they're balanced, it means they cancel out to zero. All right. Number three, when a moving object experiences no net force, all right, so now it has a velocity, and there's no net force on it. Well, Newton's first law, just like in number one, says if there's no net force on the object, it'll continue doing what it was doing. If it was at rest, it'll stay at rest. If it's moving, it will remain moving in the same way it was moving before. Nothing is changing. It'll be the same speed, the same speed and direction. Another way to say that is the same velocity. Whatever it was doing in a constant way, it will continue to do in a constant way. No net force, zero net force means the forces are balanced. They've canceled each other out. Number 4, when an object moving in a particular direction, okay, so it's moving, experiences a net force in the same direction. All right, so now it's already moving. It's moving presumably in a constant speed, in a constant direction before the net force happens. Now there's a net force that moves in the force is in the same direction as the current movement of this object. Well, the object will just accelerate in the same direction. It'll go faster and faster in the direction that it was already going. Accelerate in the same direction. The direction of the net force. And if there is a net force, if you have a net force, it means the forces are unbalanced. If the net force is 0, the forces are balanced. It's as simple as that. Number 5, when an object moving in a particular direction, okay, so the object's already moving, it's got a certain direction, it's moving along, and then there's a net force in the opposite direction. What will happen? Well, if there's a net force on anything at all, no matter what it's doing, that object will accelerate. The question is, in which direction? Well, the object will accelerate, technically. Acceleration means any change in velocity, but it will accelerate in the opposite direction of what it was doing, okay? In the opposite direction of what it used to do. What that looks like is if it's traveling, let's say it's traveling to the right and there's a net force to the left, the object will actually slow down. That's a form of acceleration. In everyday English, we would say deceleration, but it's a form of acceleration in against the direction that it is already currently traveling. And as I said before, if you have a net force, that means the forces are unbalanced. If you don't have a net force, if it's 0, the forces are balanced. Number 6, when an object moving in a particular direction experiences a net force perpendicular to that direction. So we have some velocity this way, and then suddenly we have an acceleration that's perpendicular. We actually have a force, a net force that's perpendicular, and that will cause an acceleration in the same direction. So if the direction is perpendicular to the direction it was traveling, well, in that case, it won't necessarily change its speed, but it will definitely change its direction. So the object will change direction. And because there is a net force at all, that means the forces that might have combined to make the net force are not balanced. Otherwise, if they were balanced, the net force would be 0. And this situation where you have this perpendicular acceleration, this can happen in a lot of different ways. You can imagine if you're in a car and suddenly the car turns right, the car turning right is an acceleration to the right, but your body will continue going forward. Well, if your body goes forward and your car is moving right, it will feel like you're being thrown to the left. So we experience this every day, every time we're in a car that makes a turn. Okay, looking at the next page. Now, this is something that I've mentioned in lesson 4, but I didn't give it a title. And the title I'm giving it is the 5 things all or nothing test. So this is a list of 5 properties or situations. And if you notice that any one of these is true, I am telling you that all of them are true. And if you notice any one of them is not true, then none of them are true. So it's an all or nothing test. If you see clues in a question that let you know that one of these 5 things is the situation, then all of these 5 things are the situation. And likewise, if you find a clue that one of these is not true, none of them are true. All right. So what are the 5 things? No net force, no net acceleration, no change in velocity. Velocity is constant, and we call this equilibrium. All right, so what do these things mean? No net force, it means when you add up all the forces, they cancel each other out. We say the forces are balanced, so therefore the net force is zero. So if the net force is zero, and I'll just write over on the side here somewhere, net force is zero. This is an important one. If you know the net force is zero, then the acceleration, or sometimes referred to as the net acceleration, is also zero. If there's no net force on an object, there's nothing to make the object change its motion, and therefore it has no acceleration. If it has no acceleration, there can't possibly be any change in velocity. If it was a zero velocity, it'll remain a zero velocity. If it was some positive velocity, it'll keep at that same positive velocity. If it was originally a negative velocity, it'll remain at that same negative velocity. So there is no change in velocity. We symbolize change in velocity, delta V, and that's also zero. If any one of these is true, all of them are true. Well, if the velocity isn't changing, then another way to say that is the velocity is a constant. It's not going anywhere. It's not changing. You can think of it as the initial velocity is the same as the final velocity, but it really means that none of the velocities along the way are different. They're all the same velocity. So if you see any of these, if it says it's moving at a constant rate, or it's moving at a constant speed in a certain direction, or if it's moving with a constant velocity, they all mean the same number 4. Velocity is constant. If the velocity is constant, there can't be a change in velocity. So that one tells you that's true. If there's no change in velocity, remember, acceleration is the change in velocity over the change in time. If this is zero, then this is zero too. So that has to also be true. This tells you that that's true. And what you'll learn is that according to Newton's second law, the net force is always equal to the mass times the acceleration. If the acceleration is zero, then the net force must also be zero. So one of these means all of these. And the fifth item in here is that we call this equilibrium. When the net force is zero, when the forces are balanced, when the sum of all the forces is zero, we just refer to that as equilibrium. And equilibrium has two flavors. One is called static equilibrium, and one is called dynamic equilibrium. And to a physicist, they don't care which of the two it is, but I'm going to tell you the two main situations of being in equilibrium are when the velocity is zero, it's a constant velocity of zero. That is called static equilibrium. Static means standing still. Dynamic means it's doing something. So if the velocity is not zero, it's some positive or negative value, it's constantly that positive or it's constantly that negative value, that's dynamic equilibrium. But to a physicist, these two are essentially the same thing. They behave the same way. They just have two different names. But we'll just refer to it as equilibrium. So if you hear any of these things, it means all of these things. If you hear that there is an acceleration, then that's the opposite. That means none of these are true. If there is an acceleration, then there is a net force. Then there is a change in velocity. Then the velocity is not constant. Then the object is not in equilibrium in terms of the forces on it. So what are the takeaways here? The takeaways here are, as we've said before, motion itself does not mean force. How do we know there's a force? It's when something changes. It's not about motion, it's about a change in motion. Change in motion is an everyday English way of saying a change in velocity. And a change in velocity really means a change in speed or a change in direction. So how do we get that? There are three different kinds of acceleration, and therefore there are three things net force can do. It can increase the speed, it can decrease the speed, it can change the direction. Just like in a car, you have the gas pedal to increase your speed, You have the brakes to decrease your speed. You have the steering wheel to change your direction. To a physicist, all three of these are accelerators. All three of these are examples of acceleration. Now, we don't draw free body diagrams, which we haven't done that much of yet so far. We'll do more soon. But we don't draw these free body diagrams where we have some object and maybe there's an applied force here and a weight force here and a normal force here, and maybe there's a friction force here. There might be other forces, or some of these might not be there. We don't draw these to just decorate the problem. We draw these to test the 5 things all or nothing rule. We ask, do these cancel out? Is there an acceleration in the horizontal direction? Do these cancel out? Is there an acceleration in the vertical direction? And we look at the horizontal direction and the vertical direction separately because it makes our analysis easier. All right, let's slide down to the next page here. Okay, so on this page, we're going to be looking at free body diagrams, FBDs, and we're going to use the example of an air hockey puck table with an air hockey puck on it. If you don't know what an air hockey puck table is, or an air hockey puck, it's a game where you have a table, a flat table, that has a lot of holes in it that air blows up. So a hockey puck is sitting on it, and because there's so much air blowing up from the table, the hockey puck is lifted up by a very tiny fraction of an inch, and therefore there's no friction on the puck. So we don't have to worry about friction in these situations unless we turn the air off. Okay, so you're going to see 4 situations, and you're going to be asked to consider certain questions. Are the forces balanced or unbalanced? And to answer that, you obviously have to ask, how can you tell? And what is it before and after the motion that leads you to this conclusion? So in each of these 4 problems, you're going to see 5 spaces that are labeled A, B, C, D, and E, and you're asked to do something in each of these. So in space A, you're going to label the velocity and acceleration conditions before for the before condition of the hockey puck. In other words, if there is a velocity, we'll just show a little arrow that says V. If there is an acceleration, we'll show an arrow that says A. All right. In the large box, you're going to see a large box. Draw a free body diagram for the puck, and we're going to go over how to do that. We're going to assume the air is on, so there's no friction unless it's otherwise mentioned. In C, there are 2 small boxes in the upper right section of each question, and in those boxes, you're going to write mathematical expressions for the sum of all horizontal forces. That's the horizontal net force, or the sum of all horizontal forces, and the sum of all vertical forces, otherwise known as the net vertical force. These are your net forces, and sometimes they'll be equal to 0, and sometimes they will not. All right. In addition, there's a small space labeled D, and this is where you're going to describe what's happening to the puck. Is it staying still? Is it accelerating? Is it moving at a constant velocity, etc.? All right. And then part E, you're going to see another picture of a puck, and you're going to label the velocity and acceleration conditions for the after hockey puck. In other words, after the action has happened, what does the hockey puck look like? Is the velocity 0? Is it some positive number, some negative number? Is the acceleration 0, positive, negative, etc.? All right, so let's look at these problems. It'll make more sense once we go through them one at a time. All right, so problem number 1 says a puck rests on a level floor and experiences no horizontal forces. Okay, why does it say no horizontal forces? Well, because we're not levitating the puck up in the air and we're not driving the puck down through the ground. So right now, we know there's no net vertical force on the puck. It's just sitting there vertically. It's not moving. Okay, but in this case, the puck is resting. So we know its horizontal velocity is zero. Zero. And it's not accelerating, obviously. So that's also zero. So how do we represent this? Well, if we just say this little dot is the hockey puck, and we don't have to draw the ground, we're just considering the hockey puck as a single free body object. We're only analyzing the puck. We're not looking at the ground, we're not looking at the air, we're not looking at the earth. We're just looking at the puck, and we're just going to represent it with a dot. And we're asked what forces are acting on this hockey puck that's resting on this level floor. Well, we know that there are no horizontal forces, so we don't have to worry about that. But what about the vertical forces? Well, we know there's a weight force. There's always a weight force. If it has mass, it's going to have weight. So we're going to draw a weight force vector, F sub g. Could have drawn a straighter line. And it's sitting on a surface. This hockey puck is not crushing through the earth and heading towards the center of the earth. So we know there's an opposing normal force from the ground on the hockey puck. So the weight force is the earth on the hockey puck, and then the normal force is the ground or the table on the hockey puck in the opposite direction, and that's what keeps the puck from moving vertically. We have no horizontal forces, so this is it. These are all the forces acting on this particular hockey puck. So our horizontal forces, there are none. We just write zero. Our sum of horizontal forces is plain zero. Our sum of the vertical forces is the sum of the normal force, and it doesn't matter what order you write, and just remind yourself that's a positive direction force. It's going up. This is a negative direction force going down. And when we add those two forces together, keeping track of the positive and negative signs, they cancel each other out. So we know the sum of these is also zero. Well, if there are no horizontal net forces on the puck and there's no vertical net force on the puck will remain doing what it was doing, which is it will remain at rest. And that means the puck will just keep staying with a zero velocity and a zero acceleration. And that's it for that question. Looking at question 2, the puck is moving to the right on a level floor, so it's already moving, and experiences no horizontal forces. So this is exactly the same situation as in question 1, except the puck was already moving, presumably at a constant velocity to the right. So we have our constant velocity to the right, and there's no acceleration. It's just moving to the right. All right. So how do we represent this as a free body diagram? Well, we just draw the puck as a dot. We draw any object as a dot. It could be a person, a ball, whatever. Drawing it as a dot just simplifies your diagram. And we have no horizontal forces, so we don't draw anything horizontally. And remember, the hockey puck has mass, and therefore a hockey puck will have weight. And the weight is pointing down. We know that's a downward force. And by the way, if you ever do want to calculate it, it's just m times g. And then we have the puck sitting on the table. Yeah, it's hovering, but there is a force pushing it up. In this case, actually, it's not exactly the table. It's the air blowing up. But you can think of it as the table or the air. But it is providing a normal force, a support force pointing straight up, keeping the puck from accelerating down to the center of the earth. And they're balanced, so the puck isn't accelerating up, it's not accelerating down, it's just staying there vertically, but it is moving. So just because it's moving doesn't mean there's a force. Movement is not what tells you that there are forces. Changes in movement are what tell you that there are forces involved. And this is moving to the right. There is no change. It's just moving to the right, and that's it. So we have the exact same situation in terms of forces as before. Our horizontal forces, again, are 0, and our vertical forces are the same vertical forces. We have an upward positive normal force plus a downward negative gravitational force, and they balance. So we know those add up to 0 as well. Newton's first law tells us if the puck was at rest and there are no forces, it'll remain at rest. It also tells us if the puck is moving at a constant velocity and there are no forces on it, it will continue moving to the right as it was. So the puck will continue moving to the right. See if I can get this to right. Continue moving to the right. And since I left off space, we'll just put that the velocity is still to the right and acceleration is still 0. If there are no net forces, there's no acceleration. Always, always, always. Okay, let's scroll on down to the next problem here. Number 3, while resting on the horizontal floor, the puck experiences a constant push to the right. That is an applied force to the right. So a force on an object is only a force as long as there's contact with the object. So that there has to be a constant push to get a constant force. So that's why it says constant push there. And this is just an example of an applied force. An applied force is just a push or pull that you do to an object. Okay. Otherwise, we have the same puck resting on the floor initially. So we know that initially there's no velocity on this puck. It's resting, and therefore there's a 0 acceleration as well. We draw the free body diagram. We know it has a weight straight down. That's on our negative direction. We'll just remind ourselves. We have a normal force pointing straight up. That's in a positive direction. And now we have another force. We have a constant push to the right. So there is a applied force to the right. And we'll just write that as applied. And since it's to the right, we like to refer to the right direction as positive as well. So up is positive for vertical forces, and to the right is positive for horizontal forces. So let's start adding up our horizontal and vertical forces. Well, our horizontal forces, the only horizontal force is the applied force. So our sum of all our horizontal forces is just the only horizontal force, which is our applied force. It's in a positive direction, that is to the right. Our vertical forces, as always, in this case, in these cases, is a normal force pointing up and a weight force pointing down. And we know that the is not levitating up into the air. It's not crashing through the ground and going towards the center of the earth. So we know that the vertical forces add up to 0. So our vertical forces have a net force of 0, but our horizontal force, there is a net force. So there will be a net acceleration in the same direction. So the puck will in fact accelerate to the right because that's the direction of the net force. So the puck accelerates to the right, and we represent that as the velocity is now going to the right, and the acceleration is also going to the right, or we can say the acceleration is positive and the velocity is now positive as well because they're both pointing to the right. Okay, Let's look at the last one of these questions. As the puck is moving to the right, all right, so it's already moving to the right. Someone turns off the air on the hockey puck, the hockey table. They turn off the air. Suddenly, a constant force to the left occurs. All right. Well, if you have a hockey table that's blowing up air normally from the bottom to levitate this puck, and suddenly the air comes off, well, then now the hockey puck will have a direct contact with the surface, and something's gonna happen. That something is friction. So initially, the hockey puck is moving to the right. Or we can say it's positive. The acceleration is 0 right now because it's moving at a constant speed. It's just moving. There's no acceleration, it's no slowing down, etc. Our free body diagram, as always, there's a weight force straight down. That hasn't changed. And there's a normal force up. Now you might say, well, wait, the air is turned off. Yes, the original normal force was provided by the air. Now the normal force is provided by the table itself. But there's still a normal force. The hockey puck's not going through the table, rushing, accelerating to the center of the earth. But we are told there is now a constant force to the left. Well, if the hockey puck was moving to the right, and it's now on a surface that does have friction, we would expect friction to happen in the opposite direction of movement. So this velocity vector is not part of the free body diagram. I'm just writing it in here to remind you that there's a velocity to the right. And if you have a movement to the right or a potential movement to the right on a surface where surfaces are contacting one another, then you're going to get friction in the opposite direction. So these are all our forces. There is no force to the right because nothing's pushing it to the right. It was already moving, but now it's being affected by a force to the left, the force of friction. All right. So what are our horizontal forces? Well, the only horizontal force is the force of friction, and that friction force is in the negative direction. We'll just label all our forces with our directions. So we remind ourselves this is a force to the left. Our vertical forces are the same as in every one of these problems, at least. We have the normal force up and the gravitational force down, and we know these add up to 0. So the only net force on this puck is the force of friction. Well, if it was already moving to the right, the puck will slow down. And another way to say that is it will accelerate to the left. In everyday English, we would say it's decelerating because it's going from some positive velocity to the right, eventually to 0. It's not going to go to a negative value. It'll stop moving. When it stops moving, it will stop accelerating to the left. So we have a velocity that's still going to the right. It's just smaller, and the acceleration is to the left. And another way to say that is the velocity is at the moment positive, but our acceleration is negative. So in the next video, we'll use these concepts numerically to solve free body diagram force problems.